Physical science time, we're going to learn about energy transfers and transformations, so please write that down. Energy transfers and transformations, because it's funny, Jacob.
You just said his first name.
Energy transfers and transformations. Okay, so we talked about different types of energy in the last lesson, and let's just review. Tell me, I don't know. Let's think about some types of energy. Just list them. Say them aloud.
Kinetic.
Kinetic. What else?
Gravitational potential.
Gravitational potential.
Mechanical.
Elastic potential. Mechanical. Thermal. Chemical potential. All different kinds of energy. Light was one. Electrical potential. Sound. There's a lot of different kinds of energy, right? So these two things, let's start with the basics. These two things, energy transfers are what we call it when energy goes from one object to another. So an energy transfer involves energy moving from, oops, that's not how you spell from one object to another. So what's changing in this scenario?
The surface of the whiteboard.
Yeah, good. But I mean, just when I'm talking about energy moving from one object to another, what's changing? Is the energy changing?
Possible.
Yeah, not necessarily though, right? Possibly, but it doesn't have to change the type of energy. What's changing is which object has the energy, basically, right? We'll think of some examples in a second, but before that, let's move on to an energy transformation. Energy transformation involves energy changing, what do you guess?
Into other things.
Yeah,
into other energy.
Yeah, we'll take energy changing types. So for instance, if we went, we'll think of this then, but so what would be an example of energy moving from one object to another object? Yes, Wade.
Like if the gorilla were to hit that shark, then the shark would go flying off.
Good, yeah. So if these things were a little more solid than a piece of paper, but if the gorilla, which I don't think, there's a gorilla up here. If that hit that energy, the kinetic energy in this case, would go from the gorilla to the shark, and the shark would be moving instead of the gorilla, right? So it might break my computer monitor. So an object, let's put this, an object doesn't have to be a gorilla, so let's just keep it vague. An object passing kinetic energy to another. Whereas in energy transformation, give me an example of that, not Wade. Remember, energy transformation involves energy changing types. Carter.
Would it be like light energy changing to heat energy or thermal energy?
Sure. So let's put light. This is just an example. Changing to thermal. What's a time when that might happen?
A heat lamp.
Like a magnifying glass and...
Yeah, that's a really good one. When you're about to do some genocide on some ants, and the light, the light that has come from the sun, right, which is just visible light, turns into heat when it melts the ant pile, right? Can both of these occur at once?
Yeah.
Sure, yeah. When if an object has a type of energy and passes that energy to another object where it also changes, that would certainly be, like in your lab, when we had what kind of energy to start out with in the battery?
Chemical.
Yeah, okay, it was chemical in the battery, and that changed to
Electrical.
electrical into the ends of the battery and then into the wire, which was a
And then
paper.
thermal.
And then thermal and light when that was in the steel wool. Right, so it transferred from the battery altogether, from the battery to the steel wool, and it changed from chemical altogether to thermal and light, right? So that's an energy transfer and an energy transformation. Let's think of some other specific examples of either transfers or transformations or both. So what we're going to talk about, let's phrase them in this way. We're going to have this circumstance that's happening, and then what kind of energy is changing to what other kind, and in what object is it. Wade, you've had a lot of examples here. Let's give someone else a chance.
Repeat what you said, please.
So I'm trying to think of examples of either an energy transfer or energy transformation or both, and we're going to, for that example, describe how the energy changed. So let me start out with
A
one.
car
Just
hitting
let me start out with one, and then you can have yours in a second. So let's think of just like a solar panel. So here's another example, a solar panel. What kind of energy does it start out as?
Light.
Light becomes what?
Electrical.
Sure, electrical. It's a little more complicated than that, but light energy from the sun, right? Light energy moving through the air, inside the solar panel becomes electrical energy. So this was both an energy transfer because it went from the sunbeam, which is not really a thing, but from the
Sunrise.
place, the atmosphere in this case, to the solar panel, but also was an energy transformation because it went from light energy to electrical energy. Do you remember, we just as an aside here, light energy comes in lots of different types. This will come up later on, so we might as well talk about it now. What are some different kinds of light? Let's start with the easiest one.
UV.
Sure, that's not the easiest, but I'll give you this one. Visible light. And then someone said UV, which stands for ultraviolet. They're all going to say light, so I'm just
Black
going to start like that.
Well,
That's not really one. That's actually ultraviolet light. You think it was ultraviolet? Infrared, you said, I think? Infrared. What else? We talked about these last year, so I'm kind
Thermal
of...
light.
That's infrared also. Some other ones that we talked about were microwave, radio wave, gamma.
Sound wave?
Nope. Sound waves are a different thing. X-ray, I think that's all of them. These are not in order. We could put them in order, and we'll do that later on. But these are different types of light. So anytime we're saying like, for instance, if you get sunburn, it's quite a bit more complicated than this in your body, but effectively light is becoming thermal energy. UV light specifically is becoming thermal energy in that example. Have you ever felt a sunburn?
yeah.
Yes.
Hot.
Carter had blisters once.
Nice. That's a 2nd degree sunburn then. Good job, Carter. Okay, what's another example? So you had an example you wanted to share earlier. Let's hear it.
A car hitting a wall.
Okay, good. I like that one because we're going to talk about it. So the car hitting a wall. This is an example. I'm just putting it up in an example corner. Car hitting wall. So what's it start out with?
Moving kinetic energy.
Kinetic energy. Good.
Well, actually, it's potential energy then.
Well, we're starting with when the car is moving, but you're right. We could go as far back as like saying that the car is run on chemical potential energy, right? Like it's run on gasoline, which has chemical potential energy. Well, let's just start with the motion of the moving car, okay? Kinetic energy becomes what when the car crashes?
Potential energy.
I get 3 things I'm thinking of.
Kinetic.
So there might still be some
Mechanical.
Why does it hit?
Let's just say that. Let's say kinetic as like the rearview mirror flies off or some glass shards or a tire or something, right? Kinetic, but maybe of a different object. We wouldn't call the rearview mirror part, well, it isn't part of the car anymore because it fell off. So it's still kinetic. Some of it's still kinetic. What else? Definitely thermal because, and there's a specific, we're going to talk about this in a second, but be thinking about this. This transformation from kinetic to thermal has a specific name that we'll talk about in a second. But there's one other type of energy is emitted when this happens.
Electrical.
Keep guessing. You're going to get it eventually. There's only so many types of energy.
Potential.
You already said that. Not electrical.
Gravity.
Maybe those are generated to some extent, but there's another type of energy. What would you notice if there was a car crashing into a wall?
A sound.
Sound.
Oh, yeah.
Sound. Sound. Which it would still be a sound, but not a direct transformation of energy. So kinetic turns to kinetic in a different object, which is a transfer. Thermal, which is a transformation, and sound, which is another energy transformation. This,
So it'd be like this.
under what circumstances, give me a second, please. Under what circumstances do we see this transformation specifically, kinetic to thermal?
Like in a
When what force is acting on an object?
friction.
Friction.
Friction. So write this down. This is very important. It's going to be all over your test. Friction. We already know that in forces, friction is the force that resists motion, right? It's the force that acts opposite to the intended motion. But regarding energy, friction is the transformation of kinetic energy to thermal energy. There you go. Waves got it. We did this last year. If you rub your hands together like that, the kinetic energy of your hands becomes thermal energy. You can feel the warmth. Ooh, that's
Oh, brake pads on brake.
Oh, yeah, yeah. In fact, if you've ever seen...
Formula One cars.
Yeah, I'm about to get there, Payne. You keep saying the way I was going to say it. If you've ever seen a Formula One race, it doesn't really happen in NASCAR because they're going too slow, but if you see a Formula One race and they're braking when they go around a corner, the brakes glow red hot because they've gotten so hot from the thermal energy, right? The kinetic energy of the tire moving so fast, when it's stopped, when the brake shoe touches the brake pad, there's a lot of thermal energy there, enough to make that ceramic brake pad, glow red. So there's one other specific. We're going to talk about three more things here, and then we'll be done. So I'm going to erase some of this. You have this good.
What's the thing to where they have like metal balls and then the wires and they hit each other and the other one swings?
That's called a Newton's cradle, and that's what kind of energy transfer would that be?
Kinetic.
Yeah, so it's kinetic to kinetic, right? The kinetic energy of one ball transferring to another ball. So the first thing we're going to talk about here is let's make a subtitle here: projectile motion, which we talked about in a previous lesson. Projectile motion, but now we're going to talk about it in the context of energy. Projectile motion and energy. I've had some rough times with projectiles today, but I'm going to get my ball out and hopefully it doesn't cause this to burn down.
Oh, that happened today.
Yes. Happened to you. So hopefully no one dies from this, I guess, because like I said, I've been having some rough time. This here's pantyhose ball.
Oh yeah, off of the video.
Pantyhose ball.
Off of the video
Anyway,
where you went.
Yeah. So here's pantyhose ball, and if we have pantyhose ball up high like this, and I drop it, right? We know how to describe that motion from a force standpoint, right? It has air resistance acting on it, it has gravity. But if I have it up here right now, sitting still up here in my hand, what kind of energy does it have?
Potential.
Good. Gravitational potential energy. So here's pantyhose ball. It right now has what we sometimes call GPE. What is our abbreviation for this that we use more in physics?
U.
So it has just potential energy here. As it falls, slowly what energy transformation is occurring as it falls?
It's getting from the gravitational potential energy and then.
Yeah, it's changing from, as it goes down, it's changing from gravitational potential energy to kinetic energy, right? Which means, as it goes down, is its mass changing?
No.
So we can eliminate that from the equation right away. Is the acceleration of gravity on Earth changing?
No.
No, so what's the only thing that can be changing? So there's two things. Its velocity and its height. So as its height goes down, its velocity increases, which means as its potential energy goes down, its kinetic energy increases. Just before it hits the floor, if I go down here, can you see it? No. It's just before it hits the floor, what does it have? Like when it's less than an atom above the floor, does it have any potential energy at all?
Yes.
Yeah.
So it's right here, right before it hits. When there's zero space between it and the floor, does it have any potential energy?
No, it's
No,
wrong.
it has all kinetic energy. So it's going as fast as it possibly can right before it hits the floor. Okay? Does this all make sense? So as it falls, it transfers from potential to kinetic energy. I'm sorry, it transforms from potential to kinetic energy. Now let's make it just a little bit more complicated. Projectile motion. This isn't quite a projectile yet, right? This is just a falling object. If we're having a projectile motion, which is like, okay, I'm going to try to toss this to someone. Please don't die, Alexa.
I want to catch it.
Here we go. So remember, we know that the shape it forms is this parabola. As it goes up from my hand, here's Alexa's hand. As it goes up from my hand, what's happening as it goes up?
It's gaining speed.
Try again, Wade. You're right, Carter.
It's gaining more potential energy.
Yeah, it's getting more potential energy, meaning what's happening with kinetic energy?
Going away.
Right, so what must be decreasing?
Kinetic energy.
Kinetic energy and therefore its velocity. We talked about how velocity decreases from a force standpoint in the last chapter, but now we're talking about how it's changing from, in this case, it's kinetic is changing to potential. As it goes up, kinetic changes to potential. Right here, just like in this, right here, what does it have?
Potential energy.
Only potential energy, right? When it's at the height of its path, it only has potential. Right here, when I first launched it, what does it have?
Only kinetic.
Only kinetic. Once again, when Alexa Did we catch it?
Oh, the kinetic.
Only, let's spell the word right at least. Only kinetic. Okay, what about if it's exactly halfway up?
It has,
It's 50-50.
Half and half, yeah. So 1/2 U and 1/2 K. Okay, here, the only part, this seems conceptually like it makes sense, right? Does anyone have any questions about this?
When do you have a free hour?
Wait,
So is that the reason why at the very top of the peak of the parabola, is that the reason why it looks like it freezes in midair?
yeah, it's going slower and slower up here. So I don't know, obviously because we're living in a time continuum, right, we see it then fall. So I don't know how easy it is to tell that it has frozen, but it does technically, like, for a split second there stop, and then it re-accelerates down because of what force is acting on it in this direction?
Gravity.
Gravity, specifically down. So I was about to say that the only way that this gets kind of complicated is you need to realize that at this point, okay, we'll call this A, and we'll call this B. At the K at point A is equal to the U at point B. What that means is it has the same amount, negating friction, right? If there's no friction at all, friction changes everything. But if at point A down here has a certain K, it's got that same amount of U at point B. However much energy it has stayed the same from here to here, it just changed type, okay? This will be very helpful to you on your test. There's a question on your test that I've considered for many years making just bonus because a lot of people get it wrong a lot of the time. But this, if you remember this, this will help you do good on that. Right? The kinetic energy at the bottom of something's projectile path is the same as the potential energy it has at the top if you negate air resistance. And why is that? Why does the energy stay the same? Have you ever heard of something that would make it so the energy stays the same? It's a fundamental law of the universe.
Balance.
conservation.
Say it louder, Lily.
The law of conservation.
Let's write it down in great big fancy letters. The law of conservation of what?
Energy.
Of energy. The law of conservation of energy. I'm not going to go to the bother of writing this, but I'm going to say it for you, and you're going to write it down.
Hold on.
Oh, okay.
Sorry.
Big giant letters.
Energy is never, in the universe, energy is never created or destroyed, but it can change form, right? It can change types. It can also change from one object to another. Energy is never created or destroyed, but it can change form. The law of conservation of energy. So in every one of those energy conversions we talked about, the total amount of energy stays the same. Let's think about Peyton's car example again. When the car crashed, right, it had kinetic energy of a certain amount, an X amount of car crash kinetic energy, right? It turned into three things. We said it had kinetic energy in other objects, thermal energy, and sound. If we add together all those three energies, it equals the exact same as X, the exact same as what it had before. Do you have questions about that?
Yes.
That's called the law of conservation of energy.
So can something not have the same?
Can it ever be the same after the transformation occurs? Or can
No.
it ever not be the same after
Yeah.
the transformation? Okay. So there are two cases. So first of all, a lot of people think, look, toss that back to me, please. Don't break my coffee cup. Yes, you have permission to throw it. Okay. So if I slowly, imagine, you can't see it on the camera anyway, but imagine I slowly roll this across the floor. What's going to happen to it eventually?
It's gonna stop.
It's going to stop. Did the energy go away?
No.
No, it
It
became,
just bursts in the universe.
it became thermal energy. And also another thing, listen. Sound, right? So the energy hasn't gone away.
I can
It has
smell
just,
it.
sometimes we even say that the thermal energy is the graveyard of energy, because once the energy is thermal, it can't do any useful work anymore. It's kind of gone. The universe just has absorbed the thermal energy. So the law of conservation of energy is still true in that case, right? There's still the same amount of energy. It's just changed form and the object has stopped. There is one kind of, I don't know, it's not quite exception to this. What we could do if we're being very specific, instead of saying the law of conservation of energy, we could say this. The law of conservation of matter / energy. Let's write that down. Just shove in matter above it. Because there's another thing you remember from last year maybe, and another thing we'll talk about later on in the year called the law of conservation of matter. Both of them are usually true for their respective fields. If we're just talking about energy, we can use the law of conservation of energy, and that's true. If we're talking about chemistry, if we're talking about matter, we can use the law of conservation of matter, and that's true. But in nuclear physics, we have to remember, so in some, let's write this, in some nuclear reactions, I spelled the word reaction with 2 I's, which is wrong. In some nuclear reactions, a tiny amount of matter can become a, do you know what the word colossal means?
Yeah, big.
Big.
Gigantic. We don't say the word that in here. Colossal amount
Colossal.
of energy. It is compared to the amount of matter that was transformed, it is a truly enormous amount of energy. Do you have any idea as to what equation we might use to calculate how much energy has come from an amount of matter that was changed?
Yes.
Okay, what is it? Okay, you keep going. You almost had it. Good. Oh. E equals M.
TH.
There you go. Say it again, Alexa. There you go. So write this down. E equals MC squared. Oh, you've seen it. This is looking like a real science class now. We wrote the
Albert
science thing.
Einstein!
Yeah, we wrote the science thing. It was, yeah, Albert Einstein talked about this in one of his papers. But this E, here, this is an equation you're going to have to use on your test books right now.
Are you serious?
E is energy, measured in what?
Joules.
Joules. M is what?
Mass.
Measured in
Kilograms.
kilograms. C, now here's the, oh, I love this. Here's the fun part. C is the speed of light in a vacuum. The speed of light in a vacuum. You remember talking about how capital G in the gravitational equation was a constant? This is a constant as well. We can memorize not just its units, but also what the number is. And in this case, C is equal to 3.0, you have to have this memorized, times 10 to the 8th meters per second.
Is that scientific notation?
It is scientific notation. Good observation. The speed of light, we know not just its units, but we know what it's always going to be in this equation. 3.0 times 10 to the 8th meters per second. Is this a very large number or a very small number? Use your scientific notation.
Very large.
Very large. It's going to be 3.
8 and 8.
We're going to move it
30 million.
1, 2, 3, 4, 5, 6, 7, 8. Go back and figure it out. So this is 300, say the number. 300 million meters per second. Hey, quiet please. This is how fast light moves in a vacuum. 300 million meters per second. So 1 meter is about how far I can move in 1 second if I'm just walking, right? 300 million of those every second is how fast light moves. But listen, if I took this number, what does the equation tell me to do with it? No. Careful, because I wanted you to say that, but it's wrong. Square it, which is not timesing it by 2.
Times it by itself.
Right, 300 million times 300 million. So that's a big number, right? So you see now that this tiny little bit of mass, even the tiniest, like an atom's worth of mass, multiplied by 300 million, multiplied again by 300 million, gives me an enormous amount of energy. You see that? A colossal amount of energy. That's why nuclear power plants, which does nuclear fission, and the sun, which does nuclear fusion, are so efficient. They release an enormous amount of energy every second because the tiniest little bit of mass being converted to energy is a huge amount of mass. Do you have questions about that?
No.
The end.